Hello class, I hope everyone's having a great day when they start watching this video. This week we're going to take some time to work on some skills so that we are ready for high school and even farther if we choose to go into college as well, just in some basic science skills that I think are important to have. I thought we had a whole extra week, but our school schedule got a little bit changed, so we're going to go through this a little quickly, but I think it's important that we touch on this, and we're going to start by interpreting a graph, because graphs are so important when we're talking about science. So there's lots of different types of graphs. I'm curious to just wanted to get our brains to start thinking about what we already know. How can we take what we're about to learn and apply it to what we already know? So I just want you guys to ask yourself, what types of graphs do you already know, or do you think of when you think of the word graph? So the ones I can think of are a line graph, there's a pie or a chart graph, a bar graph, and a scatter plot. So these are the ones we'll be talking about today. And then what are some important parts of graphs? We've even refreshed on this a little bit throughout the year, but some important parts I can think of is the title, the labels on the axes, the scale, and the key. So we'll be talking through each one of those. But yeah, today we just want to learn those basics, graphs, and how to read them, what they mean, so that at any time we can look at a graph and say, all right, I understand the information that this is telling me. And then we're going to practice answering just a couple simple questions from our sample graphs. This is a video that I want you guys to look at just real quickly. It's only a 2-minute video, but I think it's a good job explaining how to read graphs quickly. This is from the ACT science test, which the ACT is a standard test that people in the United States take before they go to college. So it's a time test. You have, I think, 45 minutes to answer 60 questions, so you have to go quickly. And it's really important to understand the graphs so that we don't have to read as much of the words in our charts. So we'll look at some examples later. But just to review, so our graphs typically have two types of variable. We have what's called a dependent and what's called an independent variable. The independent variable is the variable that we get to choose. So a lot of times people will be testing a hypothesis in their scientific method, and the variable we get to choose gets to be called our independent. And our dependent variable is the one that is affected by our choice. So let's think about an example. Let's say that I wanted to see how many bugs were in a certain area of my yard throughout the day. So what I get to pick, my independent variable, is going to be time. At the times I choose, I'm going to choose maybe 6 a.m., noon, and 6 p.m. That's my independent variable because I get to choose what times I pick to try to count these bugs. My independent variable will be what I measure. So what's affected by my choice, because if I chose 8 o'clock instead of 6 o'clock, it would change the number of bugs there. So it's our results. A good way to try to remember where or how we can look at a graph to find this is dry mix. So this means that our dependent is on our y-axis. We can see dry dependent responding to our y-axis. So we're always going to graph our dependent variable on our y, and our independent is on our x. So manipulated independent axes. I often forget that r is responding and m is manipulated. Those words aren't as important. What we need to remember is that our dependent is on our y and our independent is on our x. So let's look at just a brief outline of what we should be thinking about when we look at a graph. So the first thing is what's being shown. So ask what the graph is about. Is this graph about animals? Is it about numbers? Is it about population? What are we looking at is the first thing we should ask. What is being shown? Trees in Honduras, maybe, students in 9th grade, for example. What are the units on our axes? So are we looking at millions of people? Are we looking at time? What are we looking at? So ask what each unit axis is measured in. Percentages, hours, minutes, where are our units? And then the last thing is a trend. So ask how the variables relate to each other. So as one increases, what happens to the other one? We can look at maybe on our x-axis, as this gets bigger, as this variable gets bigger, what happens to our y? Does our y get bigger or smaller? Some of these trends we call as a negative slope, like this. If we get bigger, if our x-axis gets bigger while our y-axis goes down like this, we call it negative. The opposite is positive. So as we go bigger on our x, our y gets bigger, we go up. Zero relationship is just straight. So as we get bigger, really nothing happens. We stay the same as we start. And then this is a curvilinear line as well. So maybe for whatever reason, as we get bigger, we go up and then back down. So let's look at some examples. So what is being shown? Let's look here. This says the percentage of boys versus girls in attendance at a youth conventional. This also, we have another one over here that says the total number in attendance at the youth conventional. So this first one is percentage and year. So every year we have a different percentage of boys. Right here is the black and girls in the gray. So what is being shown? Our attendance at the National Youth Convention. What are our units? Oh, I jumped ahead. We have percentage and year. And then this one all the way over here is total. This number is the total number, which will be important. So what is our trend? Well, our trend looks like, at least in our total, we get more boys and girls every single year. The numbers change by percentage, but in total, they're always getting bigger. We can compare boys and girls. We can say in 1995, they were the same percentage. We had 50% boys, 50% girls. Or we can look at our total. So in we have some questions now to think about. So if you need to pause the video after and see if you can answer these questions. In 1997, were there more boys or girls? So pause the video, think about it. Let's look at our graph. 1997 is right here. Our percentage for black is higher. We have more boys than girls. So our answer would be boys. Our next question is, in what year were there just as many boys and girls at the convention? So we're looking for the year that our bars are the exact same. We can see that in 1995, they were the exact same. Our last question for this example is, how many girls were there at the convention in 1995? So this one's a little bit trickier. So this is in percentage. So we can find in 1995, our percentage was 50%. But 50% of what? Well, if we look over at our total, we can see our total for 1995 is 716. So if we have 716 times 50%, that's only 358 girls. So those are some of the questions that I want us to be able to look at and look through when we're going through these examples. Here's another one, a new graph. We're going to work through what is being shown. Well, favorite activities of people. I wish we had a little bit more information. Favorite activities of what group of people? Are we talking about kids? Are we talking about parents? Are we talking about our grandparents? What group of people? What are our units though? Well, every one of these has a percent. So our unit is in percentage and it's out of 100. Out of 100. What is our trend? We can look at a couple different trends. We can see though here, the biggest part of this pie chart is that most people like walking. That's our biggest trend here. So let's ask some questions. So a lot of times science and math kind of combine, and we can ask questions like, what is the probability that 1 out of 100 people have golf as their favorite activity? So if I were to pick out of these 100 people and ask them randomly on the street, what is your favorite activity? What is my percentage that that person would like golf? Well, I have to look at my graph. We see that golf is the favorite activity 12% of the time. So that means that 12% of the time, our probability, 12%, or 12 out of 100 could also be our percentage. So I have a 12% chance that if I ask someone, they say golf is my favorite. What about this one? What is the probability that a person's favorite activity is cycling or swimming? So this one's a little bit harder. We don't just look at cycling or swimming by itself, but we look at this part of the graph together. So if we were to add these two percentages together, that would be our probability, which would be 42. 24 plus 18 is 42%. All right, let's look at another one. This is a line graph. It's a very common line graph I remember seeing as on the ACT. What is being shown? Well, this we can see not in the title, but over here it says the solubility in grams of salt in 100 grams of H2O. So we're going to put this amount of grams of this compounds, all these different compounds. This is salt. So we'll put like 35 grams of salt in 100 grams of water, and then check the solubility. So we're seeing solubility in H2O. What are our units? We have grams of salt, and this bottom one is in temperature. The next thing is, what is the trend? Well, this has a lot of information on it, and the trends are very different. So it varies by the compound, but for example, we could say that for this KLC, or KCl I should say, potassium chloride, it's increasing, the solubility increases as temperature increases. For this compound down here, we can say that the solubility decreases as temperature increases. So there's a couple different ways we can look at it. Oh no, let me fix that. Sorry guys, we have some questions related to this. So at what temperature, or at the temperature of 50 degrees Celsius, what is more soluble? Potassium chloride or potassium chloride oxide? I don't know how to pronounce that, or this one. So we're looking at these two lines, and we have to start at 50 degrees Celsius. So we come over to 50 degrees Celsius, and then the line that we hit last is going to be more soluble. So we see that we hit this first one, this K2Cr2O7, and then we keep going, and then we hit the KCl. So we would say the potassium chloride, the KCl, is more soluble. Let's look at another one. At what temperature is the solubility of this big one equal to 30? So our solubility is over on the left side. So if we start at this line and follow it until we hit this big number, we can see at 50 degrees Celsius that that solubility is equal to 30. And what about the solubility of this potassium nitrate, I think? Oh no, that's lead nitrate, sorry. What is the solubility at 35? So 35 is in between these two numbers, degrees Celsius. We're in the middle of 30 and 40. And if we go up on our graph all the way until we hit the yellow line, it's at 70. 70 is our solubility. So I think we have this is our last example. This is a scatter plot that we're going to look at. So if we're just going to ask some questions. If the amount of sunlight was 20, about how many bacteria would be there? So this graph is about the amount of sunlight on the y-axis and the number of bacteria. So if the sunlight was at 20, if our amount of sunlight stops at 16, well, we can see a trend. As we go to the left, we go higher and higher up. So if we were to maybe extend this line all the way out to 20, I would say there would be about 0 bacteria. We might stop and run into this line if we kept going with this trend. So what kind of relationship is there between the amount of sunlight and the bacteria? This is what we looked at one of our very first slides. We said that our trend would have been negative. So if it goes down like this, we say it's a negative trend. This is one exit ticket I want you guys to try by yourself. This is a table that gives us an example here. It's just some information, and it wants us to take this table and put it into one of these charts. So we can see this says distance of ring from hydrogen chloride swab. And we can see and temperature goes up. As our temperature here goes up, what happens to our distance from our swab? Well, it stays about the same. So would that look like our A, B, C, or D? And our last exit ticket I want us to try is, what is our independent variable in this experiment? Remember, dry mix. And then at what time did the temperature increase the most? Is it from 0 to 2 seconds, 10 to 12, 16 to 18, or 22 to 24? So I just want you to try those things. When you're done, our answers here would have been D, and our answer here would have been this last one as well. So I hope that was a good lesson for you guys. If you have any questions, please let me know.